Okay, hello. For the third day of the conference, I'm Eran Arad. I'm one of the board of the SU2 Foundation, and I'm also a research fellow at Rafael. And our first talk of today will be given by Paul Urbanczyk from Stanford. And you will see soon his presentation. Paul, will you come on? Here is Paul. Welcome. Go ahead.
The floor is yours. Can you hear me okay?
Yeah, we can hear you all right.
Great. So good morning, everyone. My name is Paul Urbanczyk. I have been a PhD candidate in Professor Alonso's lab at Stanford University, working on LES and wall-modeled LES. I'll be giving this talk today in place of Eduardo Molina, who is on his way back home to Brazil, actually, as we speak. Let's see here. Before I get started, I wanted to acknowledge a few people in particular. Professor Edwin van der Weide, who spoke yesterday on the DGFEM methods in SU2, as well as Dr. Beckett Zhu, who both of whom contributed greatly to some of the work I'm going to show. And finally, I wanted to acknowledge all the members of the Stanford ADL, especially Professor Alonso, who has led and guided this research with his characteristic insight, good nature, and positive attitude. I'm going to begin today by discussing some motivation for scale resolving simulations, and then go into the development of these capabilities in SU2. Then I'm going to move on to results from a number of test cases we have run using these methods, and then wrap up with a few lessons learned and discuss ongoing and future work. So why do we need higher fidelity scale resolving simulations in CFD? Well, despite many advances in the state of the art of RANs and unsteady RANs, there are still many flows for which these techniques still perform fairly poorly. Primarily, these flows are vortex dominated, separated, and transitional flows. Unfortunately, as you probably know, higher fidelity methods like RANs and DNS are extremely expensive computationally. Thus, one of the main goals of this work is to use techniques such as hybrid RANs LES and wall-modeled LES to reduce computational cost while maintaining the advantages of high fidelity scale resolving methods. I want to point out quickly that we have seen some success with commercial codes in the space, and we anticipate this trend to continue. I believe wall-modeled LES and hybrid RANs LES methods will eventually become kind of the mainstream workhorses for turbulent CFD. Let me see here. There is a little bit of a lag, but I got it. Before I get into the development and use of the scale resolving methods in SU2, I wanted to show a bit of a hierarchy of CFD methods for the simulation of turbulent flow. As mentioned in other talks, steady RANs has been sort of the workhorse, quote unquote, workhorse for the practical simulation of real world turbulent flow for a long time. While DNS and LES have mostly been used more for idealized, canonical, or academic flow cases. However, with advances in computing power, numerical methods, and our understanding of turbulent flow phenomena, wall-modeled LES and hybrid methods are becoming more feasible, and as I said, likely represent the future for high-fidelity flow simulation. So the scale resolving methods that are in SU2 so far can be broken into two main categories. The first category consists of hybrid RANs LES methods, or delayed detached eddy simulations. In these methods, we use a function to switch from RANs to LES in certain regions of the flow where the mesh is fine enough to resolve the large energy-containing turbulent scales. The success of this type of simulation will depend on the switching function, as well as the RANS and SGS models used. Some examples of hybrid RANS LES simulations in SU2 include flow around tandem cylinders, flow through a round jet, transonic wind buffet, vortex breakdown over a delta wing, flow around automotive configurations, and flow around an iced airfoil. There are probably many others, but these are some of the highlights, some of the main ones that we've conducted over the last year or two, and I would invite you to contact the authors for more details on any of these. The second category of scale resolving flows consists of large eddy simulation and wall modeled large eddy simulation. In wall modeled LES, the LES equations are solved everywhere, including in regions with insufficient mesh resolution close to the wall where turbulent scales are small. However, as shown diagrammatically here, rather than using the under-resolved LES solution close to the wall, a second embedded grid is used to solve the thin boundary layer equations or a set of algebraic models to obtain the correct wall shear stress and heat flux. And to do this, information from the LES at an off-wall location is used as a boundary condition for the embedded grid. Equations are then solved to obtain the wall shear stress and heat transfer, and those are fed back to the LES as an alternative boundary condition. Let's see. One of the most significant parts of the wall model implementation in SU2 takes place during the initialization. When using the wall model or when using wall models for LES, what happens is the user specifies a per boundary marker exchange location. So this is a dimensional distance away from the wall boundary at which information should be taken from the LES and fed to the wall model. In SU2, when we've implemented this, when the domain is partitioned, the off-wall cell in which the exchange location is located is identified, added to the communication list, and an interpolation matrix is built. So in other words, we have for each wall vertex, we have a donor element from the LES from which the LES solution is fed to the wall model. This all happens once at the beginning of code execution. It's load balanced and it's hidden from the user, which is great. Then during the simulation, at each time step, the exchange state is updated from the LES solution, fed to the wall model, and the wall stress and heat flux are fed back to the LES. Before I get any further, I wanted to quickly address some of the limitations of scale resolving methods. These are just a couple examples. In hybrid RANS, large eddy simulations, you sometimes get turbulent eddy viscosity from the RANS, which is mismatched or much higher than the LES. Sometimes, depending on the switching function, you might have improper activation of the LES model inside regions that should be handled by the RANS. On the wall modeled LES side, limitations can occur with the SGS model, of course, which contain empirical constants. But in general, we've seen pretty good performance from the Vreeman and Whale models, which are wall adapting. But of course, there are always situations that could arise where these models might break down or not give good results. Other possible issues with the wall modeled LES can occur in very complex geometries where the user specified exchange location may fall outside of the numerical domain. For example, in cases with sharp corners. Or the wall model could fail in areas with strong pressure gradients or very thin boundary layers like you might find at the leading edge of a wing. Despite these limitations, we see a lot of promise in hybrid RANS LES and wall modeled LES, and we've seen good performance so far with SU2. with more research and advances, I believe we will see a significant improvement in these sort of limitation areas. Moving on, as it stands now, whoops, I went too far forward. As it stands now, there are a number of capabilities relevant to hybrid methods and wall-modeled LES that have been implemented in SU2. Some of these capabilities, like the Spellardo-Morris and SST turbulence models, as well as some of the low dissipation convective schemes, are already available in the main branches of the code. But much of the LES and hybrid RANS LES specific development is still contained in Eduardo Molina's branch, which is called feature_wall model LES. And my understanding is that Eduardo and Pedro are working to bring these features into the latest developed branch. So stay tuned for future code updates to see these features become mainstream. So I'm going to switch gears now a little bit and discuss some of the validation testing we have been doing. One of the first and probably the geometrically the simplest case we've looked at is that of plane channel flow. Plane channel flow is a commonly used test for turbulence simulation since the mean flow is invariant in the streamwise and spanwise directions, and an analytical solution exists with which we can compare results. We've conducted a number of studies using wall-modeled LES on the plane channel flow, and I should mention we've done these studies both with the finite volume solver in SU2, as well as the discontinuous Galerkin finite element method solver that Edwin van der Weide discussed yesterday in his talk. Some of the findings for the finite volume solver are shown here. In particular, on this slide, we can see the influence of the exchange location on the performance of the wall model. In general, it is recommended to place the exchange location at approximately 10% of the boundary layer thickness, and then refine the LES mesh such that this falls above the third or fourth point off the wall. And those are just sort of a general guideline, and you can see in this plot the effect of the exchange location on the log layer match given in the plane channel case. So one other thing we looked at, in addition to wall model exchange location, was the numerical schemes in the plane channel flow case. Specifically, we looked at kinetic energy and entropy preserving or KEEP schemes. And those schemes are mentioned, some of those schemes are mentioned here. We first tested these schemes on the inviscid Taylor-Green vortex case, which you can see in the left-hand plots. And then we applied them to the wall model, or the plane channel case, and you can see some results over here on the right. You can see that the KEEP schemes seem to show a better prediction of some of the turbulent fluctuations, even though maybe not necessarily as good or the same match to the mean velocity profile. So because of this, whenever possible, we recommend in SU2 using either the modified JST convective scheme or the SLAU2 schemes. Moving on, the next case I'm going to talk about briefly is a rather complex case of flow around a nose landing gear model. This is known as the lagoon model. In this case, the acoustics of the flow were of interest with both static and unsteady pressure measurements taken, as well as the collection of PIV and LDV data. You can see here the mesh, some of the details of the mesh. It was generated using pointwise. You can see the overall mesh structure and refinement in the figures. In this case, we did run into one of the issues I mentioned previously, where the specified exchange location was not properly found, probably because it lay outside the domain. When this happens, I should mention the exchange location is set by the code to just be at the first off the wall point. This isn't great, but it's not that bad. Fortunately, in this case, this only occurred for 2 of the wall vertices and really didn't cause any major problems. You can see here some comparison or values for the computational cost, generally pretty good when compared with some of the other simulations that were performed on this case. In this particular case, the wall model LES was a bit better than the DDS in terms of wall clock time, but both were reasonably comparable. You can see in this slide some of the results, the DDS on the left and the wall model LES on the right. You can see the vortex shedding by both methods, as well as the Y+ surface field, which serves as sort of a proxy for the instantaneous wall shear stress. Obviously, the wall modeled LES shows sort of the turbulent or resolution of turbulent eddies in the boundary layer, whereas the DDS has more of a RANS-like boundary layer behavior. In general, for this case, both the DDS and the wall modeled LES perform quite well in terms of the surface pressures and pressure spectral densities. The results were also fairly comparable in terms of the wake velocity profiles, with the wall model LES outperforming the DDS in some areas and vice versa in other areas. In general, though, we were fairly happy with the performance of these methods in the lagoon case. For additional details, there's a lot of other results that I'm not showing here. I'd refer you to Eduardo Molina, who can discuss a lot of the nuances of this case in greater detail than I can, or that time allows. Another case performed with the scale resolving capabilities of SU2 is the JAXA standard model. This case was used as part of the third high lift prediction workshop, where a number of different simulations were performed by academic and commercial groups. The test case is shown here with both nacelle pylon on and off, but for our simulations, we kept the nacelle pylon off. Here you can see some of the mesh details. For our simulations, Eduardo created the mesh using pointwise and its voxel core meshing capability. He tried to keep to the practices outlined in the workshop for a close to apples comparison. And note that we created two meshes, G1, which was a little coarser, and G2, which was a more refined or finer mesh. Here's our some of the results. You can see, lift and moment and drag coefficients plotted. I do want to address that in this case, Eduardo implemented a slightly modified algebraic wall model. This wall model was meant to include effects of adverse pressure gradient. It's called the adverse pressure gradient log law wall model. For more details, you can check with the citation, although I need to double check with Eduardo whether that's actually the right citation. I thought it was by a different group. But in any event, you can see that in general, the best results were obtained with the Vreeman SGS model, coupled with the adverse pressure gradient log law wall model. And those are the points in red in these plots. We assessed the flow at a few angles of attack. Here is just one of them. And you can see the pressure coefficient plots at various wing stations. In general, the wall model LES is performing quite well here. And particularly if you look at the tipmost station, you can see that with the fine mesh, the Vreeman wall model, and the adverse pressure gradient log law model, we're doing a very good job. This slide is really just sort of some pretty picture and shows flow structure over the wing. Bear in mind on the right side, you see surface Mach number. You would expect these ordinarily in a resolved simulation to be 0, but bear in mind that use of the wall model changes the boundary condition from a no-slip condition to a shear stress condition. And since the first cell of the LES is relatively thick, it is actually expected to see the non-zero flow at the surface. Moving on, one of the more recent tests, and I realize I'm getting close to my time, so I'll try to hurry up. One of the more recent tests we conducted with SU2 was simulating flow through a serpentine diffuser. These types of diffusers are of interest for unmanned aerial vehicles with offset engine geometry. In this particular case, we were looking at flow through a double turn diffuser. The simulated flow rate that we used was the highest used in the experiments, which were conducted at Georgia Tech. At this condition, the flow becomes sonic near the throat area, then separates over the bottom after the first turn, and separates at the top surface after the second turn. So it's a fairly complex flow. Pressure data was taken at the AIP, which is the aerodynamic interface plane, and was used to generate total pressure recovery, distortion, as well as approximated flow rate. You see here a quick slide just showing the meshes used. I don't want to spend a lot of time, but really the only difference between the fine RANS / DDES mesh and the wall modeled LES mesh in this case was the thickness of the first wall cell. And here you see some pretty pictures or animation. I wish we had taken the time steps a little closer together so this was a little smoother, but that's a lot of data. But in general, you can see kind of how the flow behaves throughout the duct and at several streamwise locations through the duct. On the right-hand side, you'll note that we did use SU2's RANS capabilities in addition to the scale resolving simulations. And you can see there's quite a difference between the RANS results, the DDS result, and the wall modeled LES results. We ran all of these simulations on DoD unclassified systems with varying numbers of cores, and overall the performance was pretty decent. These simulations were doable in realistic amounts of time. Oops, so I'm getting close to the end. I'll try to wrap up. Let me advance. To sum up kind of the ST2, you see that our wall modeled LES results are kind of the best out of the SU2 simulations and very closely match the results with the experiment and Boeing's in-house CFD code, which was used to do a DDS. I had one more case, but I'll skip kind of most of this introductory slide. Suffice it to say that we also looked at flow through a high aspect ratio rectangular nozzle, and we used both the RANS and wall modeled LES capabilities of SU2. The results were quite good, very promising. You can see in particular close to the nozzle exit, the wall modeled LES does a very good job. Looking back, we do think that if we maybe extended the mesh refinement region a little further downstream, we would have gotten better results away from the nozzle using the wall modeled LES, but maybe this is a candidate for some of the higher order methods that Edwin discussed yesterday. You know, of course, there are plenty of other test cases that have been run using SU2. I encourage you to contact Eduardo if you'd like more information on any of them. And we wanted to kind of close with some guidelines for some of this, how to run some of these scale resolving simulations in SU2. Some of the tips or advice on numerical methods, the mesh generation guidelines, spatial discretizations, and time step, a choice of time step. And you can see sort of the corresponding parameters that you would use in the SU2 config file here on the right. And finally, getting to some of our future work, I think, you know, as I've said, the scale resolving capabilities within SU2 are still a work in progress, but the contributions should soon be merged into the main branches. I think there's a lot of promise here. In future work, I think, you know, some of the most interesting possibilities for research would be enhanced wall modeling, shock capturing, and enabling kind of sliding mesh or moving mesh applications. I know I kind of went quickly through some of these last slides, but that's the end of my talk. If there are any questions or comments, now is the time. Thanks very much.
Thank you, Paul. It was amazing, and it's a pity that you had to hurry in the end with such interesting talk. There were two questions were raised, one by Matteo Pini. Thanks for the very informative presentation. Great work and kudos to all the teams. Just one question. Our high-order numerical models are also available for solving incompressible flows. I guess it means not only high order, but the LES methods.
That's a very good question. I don't believe that the wall-modeled LES and hybrid RANS DDS or hybrid RANS LES methods are in the incompressible flow solver at the moment. But for most of these questions, I'm going to have to refer back to Eduardo Molina. I'm happy to put our heads together and we can get back to you with a definitive answer on that. But my understanding is that no, they are available only in the compressible side.
Okay, and Pei Defana asked, I have two questions. The filtering in the hybrid RANS LES is implicit or explicit? And second, for wall model LES, I guess, how do you find the HWL, whatever they are, HWL?
So the filtering, I believe, is implicit. It's based on just the mesh spacing, but I will double check with Eduardo on that.
I think you mentioned Vreman in certain part, isn't it?
I'm sorry?
I think you mentioned Vreman subgrid scale.
The Vreman SGS model, yes, is used. Oh, I see. So yeah, implicit LES versus explicitly SGS model. Yes, sorry, we do have subgrid scale models. We are not using the LES in sort of an implicit mode. These are supposedly physics-based SGS models. Yes, that's good.
Okay, so thank you very much. We'll have to stop here and go for the second one. It was a very interesting and